A QR code with company logo in the middle of it. Point a phone at it and the link comes out. Tear the bottom right corner off, same link. You are thinking the scanner just guessed the rest. It did not. About 60 squares in every 100 were never your link. They were worked out from your link and printed alongside it, and the logo is sitting on some of them. Keep going, take another corner, take a strip out of the middle. At some point, the code stops working. What you get then is nothing at all. A guesser would hand you something. This code has worked out that it cannot rebuild your link exactly, so it gives you nothing. That guarantee is expensive. 60 squares in every 100 is a lot of paper to spend on something that is not your message, and nobody pays for that by accident. This code was designed in 1994 by a 2% team at Denso Wave, a company inside Toyota's group, led by an engineer called Masahiro Hara. It was designed for a box of car parts. A barcode is the row of stripes on the side of a packet, and it holds about 20 characters. A box of car parts needed more than 20. So some boxes went out carrying as many as 10 barcodes, and a worker scanned them one at a time, sometimes thousands of times a day. Toyota's plants ran just in time. Parts arrive as they are needed instead of sitting in a storeroom. So a box still being scanned is a box that has not arrived. And there was a second problem with the stripes. They could not hold a Japanese character at all. So the fix everybody reached for was a code that holds more, and the other companies were already building them. Two-dimensional codes, squares in a grid instead of stripes in a row. Denso Wave's own history of those years says the team building them were all obsessed with the same thing, packing in as much information as they possibly could, and it worked. Capacity stopped being the problem. Holding more was never the whole job, though. You would think the hard part is fitting the information in. It is not. The hard part is finding the code at all. That is the strangest part of this story to me. A barcode scanner is a laser pointed at a stripe, and a person does the aiming. A camera looking at a parts box gets the whole box, print, labels, oil, and whatever angle the box was stacked at. Somewhere in that picture is a code, and nothing can be read until it is found. So Hara's team went looking for a pattern a camera could spot instantly and would almost never run into by accident. They surveyed printed matter, pages, labels, packaging. They measured how the blank and the white alternate across all of it. One proportion came up less than any other, 11311. A black bar, a white gap, a black bar three times as wide, a white gap, a black bar. They built a square out of that proportion and put one in each of three corners. Find those three and you know where the code is, how big it is, and which way up it is, any angle, any direction. The code they designed could be read more than 10 times faster than the other codes of the day. The Q and the R stand for quick response, and the 10 labels on that parts box came to about 200 characters between them. The one code that replaced them holds about 7,000 digits. Fast, findable, and anonymous was still not enough because of where the code was going. It was going onto a cardboard box in a car plant, scraped along a rack, smeared with oil, torn on a corner. A label that will not scan stops the box, and a stopped box is the exact thing just in time exists to prevent. So the code was given spare squares. Nenso Wave publishes four settings for how much spare room a code carries, and their own advice is plain: the strong settings for a factory where codes get dirty, the weakest one for a clean office where you would rather spend the room on data. So look at what is inside one. Inside is a short piece of text written out as squares. Your link, I have been calling every one of them a square, and that has flattened a real difference. The three big ones in the corners are the pattern from the survey, and the smaller marks around them go with it. Their job is to let a camera find the code, work out which way up it is, and line up the grid. Everything else is two piles, your message and the spares that are keeping it alive. Your instinct here is to print the whole thing twice. It does not work. Damage can take the copy too, and nothing on the paper says which of the two is right. Copies are the wrong idea. What works is a different kind of drawing. Your link becomes a shape. Every square on the code is one measurement of that shape, taken from a different spot. I'm going to shrink that down to the smallest version there is. Put two dots on a page. Exactly one straight line passes through both of them. Only one. That line is the shape, and two dots carry the whole of it. The scanner can draw the line from those two dots alone. Now there are 10 dots instead of 2. 10 is a choice. about how much spare you are willing to pay for. All 10 sit on the same line, two of them are your message. 8 are spare. I have made that far more generous than a real code on purpose because it makes what happens next easy to watch. And those 8 spare dots cost paper, exactly the way a code spare costs paper. Rub 8 of the 10 out and take both of the dots that were your message with them. Two spares are left and the line is exactly where it was. It has not moved by a hair. Both dots you wanted belong exactly where they were, and you can put them back. Every dot on that line was a statement about the whole line, not a copy of one part of it. That drawing has a limit though. Your link is a long row of numbers, and every one of them is written into the squares you're looking at. The program that builds a real code does the same job with arithmetic. There is no dot anywhere in it. I have simplified that on purpose because one thing survives the simplification, and it is the part that matters. Any big enough handful of the squares rebuilds the whole message. The scanner has a harder job than that. It does not know which squares are wrong. Rub a dot out and you can see something is missing and one square covers it. Move a dot off the line instead. The moved dot still looks like a real one and nothing about it says it is lying, so it costs two spares. One to notice that no line fits anymore, a second to work out which dot moved. The people who invented the code published a figure for each setting, and a setting is how many spares go in. The code is on the strongest one. 60 squares in every 100 are spare. So you would expect a code to survive 60 damaged squares in 100. Two numbers here set, one halving apart. And I want to be exact about which is which. Damage that shows costs one spare each. Damage that lies costs two spare each. But every damage square has to be treated as a liar. 60 divided by 2, that is a 30 in 100, and 30 is the figure they publish. 60 squares in every 100 were never the message, and they were worked out from it. Every one of those squares describes the whole message. Any big enough handful rebuilds it. The code cannot tell an honest square from a lying one, so half of that budget goes on working out which is which. You are picturing your logo as damaged and the code as the thing that forgave it. The code in front of you was never a complete thing that got damaged. It was printed with far more squares than your link needed long before anybody was putting a logo on one. The room your logo is sitting in was there before your logo was. That room was built for a parts box that was going to get scratched. All of this has a name. It is called error correction. The method a QR code uses is called Reed Solomon after the two people who published it in 1960. So the next time a code refuses to scan, you know what it is telling you. It cannot rebuild your link exactly, and it would rather hand you nothing than hand you the wrong one. Alright, if you liked the video, make sure you like and subscribe. Thank you for watching.